Hello, I aim to introduce this alternative student learning resource on 3D plane stresses and strains via this video. These topics are taught under the Engineering Mechanics Statics and Solids Mechanics modules during the first and second year, respectively, of an engineering course at Queen Mary University of London. In particular, mechanical, aerospace, and medical engineering. This project was part of the QProducers program, uh, overseen by Tim Morgan and offered to students who feel that they can make complex topics more easier to understand by creating learning resources that adopt different techniques to those currently available to students. QProducers also enables participants to work with the academics and module coordinators of their chosen modules to provide guidance on the accuracy of their learning resources and critique on the effectiveness of the learning mediums chosen. In my case, this was Dr. Emiliano Bilotti, who is the statics module coordinator. Here we have the first slide of my learning resource, and this just provides a brief introduction to what this learning resource concerns, aims and objectives to be met, and how they will be met. You would have noticed the Lego tower in the background. I'll just scroll back. I thought this was a good representation of how one progresses in statics related modules, or any mathematical or physics-based topics for that matter. To progress onto and understand more complicated mathematical methods, you need to make sure that your foundations in the basics are strong, so that you can build up this tower of knowledge, if you will, without becoming confused along the way. Now, the presentation makes use of many custom animations, most of which automatically start after each other. And to make the most of them, particularly when variables are coming together to form equations, which you'll see later, it is important to establish that round of animations have finished before hitting the space key. And then there's 5 boxes on the top of each slide to give an indication of how far into the topics you have progressed through. So we'll start off with the subtopics under stress analysis. Further to what was mentioned before, I thought it was a good idea to provide students with the basics of each major topic just to refresh their memory. Now, what we're asking here is for students to imagine some 3D shape. I'll make a mention of the assumptions a little later. Where if we cut this 3D arbitrary shape and we reveal 3 internal surfaces, we can see that a whole internal network of forces exist. And rather than considering the whole volume itself, we can isolate just one elemental volume here that is a unit representation of the forces acting on the whole volume itself. And if we enlarge that elemental cubic volume, we can see the various stress terms acting on it. And this is really the unit of the whole 3D volume we initially considered. And it ties in with some of the main assumptions I included earlier. So if I scroll back. So if we imagine that our 3D arbitrary volume has millions of those cubic elements connected together uniformly, so that the density remains constant. So if I forward again, So here I show how the main types of stress differ. We'll start off with normal stress, also referred to by this sigma variable here. Its definition is outlined by this equation. And if the limits are implemented, we end up with the basic equation for stress, force over area, the units of which are pascals, since this is also the basic equation to calculate pressure. Shear stress, represented by the tau symbol here, is slightly different. The main difference is that the shear stress acts along the surface of a 3D shape or the tangent of a 2D shape rather than at 90 degrees as normal stress does. And therefore, it is the intensity of the tangential force acting on the small surface area of our elemental volume. We obtain the following equation if we consider the tangential forces acting in the x direction. Now we can move on to general stress state, which is a case represented here by that schematic. And you'll notice that all of the variables have subscripts, and there are different rules for normal stress and shear stress subscripts. For normal stress, the subscript is simply the same letter as the axis along which the normal stress runs along. So with this one, where the cursor is pointing, the normal stress runs along the z-axis, so the subscript is just z. With shear stress, the first letter of the subscript is the axis to which the shear stress is perpendicular to. So it's at 90 degrees to that axis. So with tau zy here, z is the axis to which this shear stress is acting perpendicular to, and the second letter is the axis to which the shear stress runs along. So let's bring back the representation of general stress state. So what we're essentially doing here is taking a 2D slice from our element and just considering the stresses on that. Note that because it is two-dimensional, there are only two directions on which the stress terms act along. And if we rotate this plane by angle alpha, we end up with a different coordinate system, x prime and y prime. And now direction cosines can be derived by the following setup. And when the plane does rotate by angle alpha, we obtain a direction that is normal to this tangent. The normal axis here, and we have the x prime axis, and this is normal to the tangent or to the tangent of the oblique plane for the 3D case. And the angles beta and gamma are the angles made between the normal axis and the y-axis, and the normal axis and the z-axis, respectively. the direction cosine expressions themselves are formed here and define plane orientation. Now we will apply this to the 3D case. Imagine the cubic element introduced a couple of slides ago. Now imagine that we remove some material to leave a shape with a triangular oblique plane, like so. The different stresses acting along each surface of this shape can now be considered, and we can let the area of the oblique face, which is this face over here. I can get my cursor to hover over it. Unfortunately, my computer is rather slow today, so can't see the animations to their full glory. But here, yeah. So the area of this oblique face here is delta A. And previously we mentioned that the stress is equal to force over area. So if we multiply stress by the area, we are effectively left with the force. And this allows only forces acting on the triangular base pyramid to be considered and resolved. So now we can see where the normal stress and shear stress exists on the oblique plane in respect to the stresses acting on all the other faces. And what we're saying here is that there is a resultant force acting in each direction. And as mentioned earlier, to get the force you multiply the stress. And here we have S for the resultant stress. And the expression for S, the resultant stress, is derived from Pythagoras' theorem, as we can arrange the normal stress and shear stress to form a right-angled triangle, like so. As promised, we'll resolve forces along the three axes we have here, x, y, and z. So starting with forces along the x-axis, for static equilibrium, the sum of forces in the x direction needs to equal 0. So now we multiply the lengths L, M, and N with their constituent forces. And let's remember that the forces here are equal to the resultant stress S in the x direction multiplied by the surface area of the oblique face. Now we apply the same process to the other directions. So forces along the y-axis and the z-axis. And if we cancel out the delta A term here, we end up with the following set of equations here. And these can be rearranged into matrix form, also known as the stress tensor. For the three-dimensional case, the stress tensor is a 3x3 matrix. 2 dimensions would correspond to a 2x2 matrix, and 1 dimension denotes a vector, so simply a magnitude of stress and its direction. Quick note about the 2D case, the stress tensor for which would only include these terms here. So in fact I could highlight that just to show you. Yep, so that's for the 2D stress tensor. And to help you remember where each of the variables in the stress tensor goes, just remember that it's symmetrical along this normal stress diagonal. Yep, I even included a note of that there. The Morse circle, which has just appeared now, is just another method that can be used to calculate various stress values and principal stresses. And the principal stress of which I've included here, here, and here. And during this project I collaborated with a material science student, Joya, who created a resource that covered other statics aspects, and her resource details how the Morse circle can be used, so be sure to check that out as well. And again, since this is the 3D case, we have 3 principal stresses which appear on the Morse circle, and they occur when the shear stress tau is 0, and our stress tensor reflects that change as well. The resultant stresses in terms of the principal stresses are as follows. So these equations here we derived 2 slides ago, and what we can do is equate these 2 sets of equations into each other because of these common variables. There. These equations can be rearranged to obtain these 3 equations, and these can be written in matrix form. And a good way of how to remember this is to start with the normal stress terms, going down diagonally from left to right, then place all the stress terms either side. Essentially all we're doing here is removing the plus signs and separating the stress terms from the lengths L, M, and N. we obtain this equation by finding the determinant of this matrix. And the stress invariance I1, I2, and I3 can be calculated as follows. You would have noticed I've tried to use some recurring color themes, in particular blue for normal stress and red for shear stress, just to help aid memory and acknowledgement of the patterns that exist in solid mechanics. Here, for example, we have neon green for the X subscript and orange for the Y subscript. The hope is that this will help students notice where the subscript here, let me get my cursor to appear, where the subscript here is X, and when this is Y, the subscripts for shear stress would be XY. And the same applies for all other terms as well. So sigma X and sigma Z, that corresponds to tau XZ, or sigma Y and sigma Z, tau YZ. So if we just bring back the expressions we introduced in the last slide, I have included some brief details of what the stress invariants entail. The axis along which stress acts does not affect them, and it is also important to note that the principal stresses do not change with a change in the orientation of the plane. We can simplify the expressions for I2 and I3 and actually find the determinants, and we can obtain the following equations. For further details on the implications of these stress invariants, I recommend you check out this link here. We now move on to strain analysis, which bears many similarities to stress analysis. Starting with the basics, as we did for stress, here we ask students to imagine a bar with original length L and a force applied to either ends axially. And it is expected that the bar will deform by a certain length delta x here. And from this we derive the basic strain equation. Change in length over the initial length. If we think of the load resulting in normal stress, the strain, epsilon, can be represented by this equation here. There is another significant variable known as the Poisson's ratio, which is simply the strain in the transverse direction of a material divided by the strain in the longitudinal direction. Good, easy to remember, but this doesn't explain why we have a negative sign here. Well, tensile deformation is positive, whereas compressive deformation is considered to be negative. And negative overrides positive in mathematics, so we end up with a negative equation overall. And since most materials tend to become thinner, in the transverse direction, so a negative length change as they are being stretched longitudinally, they end up having a positive Poisson's ratio. And this animation here shows that very clearly. We introduced this Hooke's law equation from the last slide. So where we have tensile stress applied in the x direction, there will be compressive strain in the other directions. So the strains in the y and z directions have a negative expression that includes a Poisson's ratio multiple. And the same applies for the other directions as well. If we bring back those equations, note the differences and similarities amongst the equations in each set. By the principle of superposition, each set of equations for the directions can be replaced by one equation, like so. As we have normal and shear stresses, we also have normal and shear strains, and these equations are used to calculate normal strains. The most simplest case for determining shear strain can be seen here with this schematic. The square deforms into what looks like a rhombus by lengths delta x and delta y, and if the sum of these lengths are divided by the initial length of one side of the square, which is t, then the shear strain, denoted by this gamma symbol here, can be found. However, this equation only holds true for strains that are very small. So for general cases, the following equations would be more appropriate. So now we move on to our final subtopic under strain analysis. And like the stress tensors, the strain tensors have the normal component strains going down this diagonal, and the shear strains are here, which I'll just highlight. So here are the shear strains, which I'm highlighting here. And the stress terms can be replaced by corresponding strain terms in equations and matrices, and the following variables key is useful for that matter. Well, that is all of my resource. Thank you for watching, and I hope this has been insightful. Unfortunately, my computer was rather slow today, so the animations took a while to take effect. So if you wish to view the presentation yourself, feel free to. The link can be found in the description.